Can you see my screen?
Yeah.
Okay, cool. I mean, it's recording for now until it decides it doesn't want to. So what I wanted to do is I wanted to go over a couple of the problems from 32 and 34 with you, and then let you guys kind of break up into groups. So let's look at 32a from chapter 5. Because it's important that eventually you get comfortable with recognizing stereochemical relationships and with actually assigning stereocenters. So 32A has one molecule that looks like that. And another molecule that looks like that. And it asks you whether those are enantiomers, diastereomers, constitutional isomers, meso compound. So what's the stereochemical relationship between those two compounds? So you'll notice that they are mirror images, right? There's a mirror plane there. So the question is, are there any chiral centers in that molecule? And then the other question is, are those two mirror images superimposable, right? We want to determine whether there are chiral centers in the molecule, and then we also want to determine whether the molecule itself is chiral. So how can I tell whether there's a chiral center?
Look at the substituents.
I'm looking at the substituents, right? So I'm focusing on this carbon, the central carbon. CH3 is never going to be chiral, right? Because the CH3 has 3 identical hydrogens. So on this carbon, what's attached?
2 CLs, an ethyl group, and a hydrogen.
And as soon as you say 2 Cls, what does that tell you?
It's not a chiral.
It's not a chiral center. Right? Which probably means it's superimposable on its mirror image. It's possible, obviously, right, to have chiral centers but not be chiral. It is, in fact, also possible to be a chiral molecule even in the absence of a chiral center, but usually you have to have some kind of twist in a molecule, like a ring fusion where 2 rings are together, like something like this. It's a kind of contrived system, right? You've got to have something in the molecule that twists it. So this molecule is chiral, even though there's no chiral center. But because, right, this substituent here is identical to this substituent there, so this isn't a chiral center, but there is a twist in that molecule, which means it won't be superimposable on its mirror images. But that's relatively unusual, right? There's got to be something in the molecule that twists it out of plane, and there's nothing in this molecule that twists it out of plane. So you can superimpose that on its mirror image by simply rotating the molecule around this axis, the y-axis. And if you spin the molecule on the y-axis, this chlorine that was behind becomes this one, and this chlorine that was up front becomes that one, and those molecules end up being superimposable. So let's take a look at B. Right. It's a similar molecule. Got a CH3, a hydrogen, and then we have a chlorine up and a fluorine back. And then if we look at the other compound, looks like this. All right. So the first question is there a chiral center in that molecule? And then we have to decide whether the molecule itself is chiral. Any chiral centers?
Yeah.
Yes. Yeah. Right?
Yep.
That's a chiral center. Usually we mark that with an asterisk because chlorine, fluorine, CH3, and hydrogen are all different. So now we have to determine whether it's superimposable on the mirror image. Or, alternatively, we could actually label that chiral center as either R or S, and if it turns out to be the same, then we know that the molecule isn't chiral, right? Because the stereo center is the same. And if it's the same, then we'll be able to superimpose it on its mirror image. You can probably already tell by looking at it that if we were to rotate 180 degrees around the y-axis, the fluorine which was in the front will go back, which will overlap with that one. The chlorine which was in the back will overlap and be on top of that one. So this is actually identical, just as the other one was. But this, in this case, it's an identical molecule because it's the same enantiomer. There is a mirror image that wouldn't be superimposable if I drew this compound. Right, which is the mirror image on a different plane. This would end up not being superimposable because if I dragged it up so the CH3 and the hydrogen were on top of each other, the chlorine would be where the fluorine is, the fluorine would be where the chlorine is. So this is an enantiomer. You had a question?
Yeah, for the mirror image,
yep.
Shouldn't the fluorine still be going back and the chlorine coming out?
The way the textbook has it drawn is the way I showed it, right, with the fluorine up and the chlorine back. But obviously if you rotate it, right, if you spin it 180 degrees around that y-axis, then it becomes the same molecule. But these are the way they were written in the text, and then you're being asked whether it's an identical compound or the mirror image. I could write the mirror image this way too, right, by switching these two, and then it would be the mirror image on this plane.
Mm-hmm.
So the question is that an R or an S stereo center? This one, since it's the enantiomer, will be the opposite. And this one, since we've determined that you can rotate it 180 degrees and it'll overlay itself, right, the chiral center will be the same in these two. So how do I determine whether it's the R or the S stereo center? What do I need to do? Feel free to chime in there. Don't make Adrian do all the talking, unless, of course, he wants to.
Down the hydrogen bond.
All right, so the hydrogen is substituent 4. Right? I need to know which is substituent 4 so I know which bond to look down. So the first thing I should do is number the substituents by priority. Sometimes there's not a hydrogen, right? So something else might be substituent 4. So what's substituent number 1? What's the highest priority substituent?
Chlorine.
Chlorine, because it has the highest molecular mass. What's next between fluorine and carbon?
Fluorine.
Fluorine. And it doesn't matter what else is attached to this carbon. In this case, it happens to be CH3, and CH3 has a molar mass of 15 and fluorine is 19. But even if this were like a propyl group or something else like 43 or a butyl, which would be 57, it's the first point of attachment. So the fluorine would still outrank it. Right? So I can number those. And then I need to look down this bond from the carbon to the hydrogen and trace an imaginary circle from substituent 1 to substituent 2 to substituent 3. And if I trace that imaginary circle like this, am I going clockwise or counterclockwise? Clockwise. So that would be R or S.
R.
R. Right? This one would also be R. I'd be looking kind of a different perspective. So I'd be going from 1 to 2 to 3 like this. That's still a clockwise rotation, so that's R. So I could, instead of worrying about whether the mirror image was superimposable, I could have started looking at the chiral center, labeled this one as R, labeled that one an R, and say, oh, okay, that's identical. Since that's the R stereo center, it must be the same molecule. This one obviously will be S, because the chlorine and the fluorine are in different places, which means when I trace my imaginary circle from 1 to 2 to 3, while looking down the bond from carbon 3 to the hydrogen, that'll be a counterclockwise rotation. So that's S. So it's important that you number your substituents correctly, because if you number the substituents wrong, you will generally end up with the opposite stereocenter. And it's important that you look the right way down the bond. It has to be from the carbon to the fourth priority substituent, not the other way. If you do both those things wrong, they will be the two errors will cancel each other, and you'll get the right conclusion, but not for the right reason. Right? So let's look at problem 34. And look at 34A. And this time it's written as a line structure. And we've got a CH3 or an H3C. I've written it the way the textbook writes it. And we're asked to identify any chiral centers that would be present in there and label them as R or S. So what will we be looking at? See if I can get a little bit more light on there.
Carbon with the CH3 and H group attached.
So that's the chiral center. Generally, if you have solid wedges and dashed wedges drawn in a molecule, that's kind of a tip-off that that might be a chiral center, because if it's not a chiral center, you often don't show the front and back substituent. That's not true, especially in this chapter, because in this chapter they're trying to fool you. But most of the time when you look at a structure of a molecule on Wikipedia, for example, if you see dashes and wedges like this, that's probably going to be a chiral center. So we have one chiral center in this molecule. How do we number our substituents?
4.
Okay, so you jumped immediately to saying it's R, which is correct. But probably we should number our substituents first.
I said hydrogen is 4.
Hydrogen is 4. If there's a hydrogen, hydrogen is always 4.
How did I jump to that it was R?
Oh, I thought someone said R.
Oh.
Which is right. It's the correct answer. So hydrogen is 4. All 3 of the others are carbon.
The carbon with the methyl group, so C2, is going to be number 1.
So this carbon is going to be number 1. Because this carbon is bound to 2 other carbons and a hydrogen. Whereas this carbon is bound to just 1 other carbon and 2 hydrogens, right? So it doesn't differ at the first point because they're both carbon, but at the second it does, because 2 carbons outranks 1 carbon. And then CH3, right, that's a carbon that's not bound to any other carbons, so that would be number 3. And we're looking the right way down the bond already because the hydrogen is written back. That's kind of convenient. If the hydrogen's written out, it's a little more challenging because you have to mentally put yourself back behind the page. So this is another one where you have that clockwise imaginary circle, right? And so that's the R stereocenter. Let's take a look at 34I. That's a cyclic structure. And it's got a ketone here. Got a hydrogen there. And an NH2 group. Put the lone pairs on just for completeness. So what are we looking at in this one? Obviously there is a chiral center in all these molecules. Go ahead.
The carbon with the NH2 group and hydrogen on it.
So not surprisingly, the carbon where we actually have a solid wedge and a dashed wedge, right? Because if you don't have that solid wedge and dashed wedge, then you don't have the relative positions of the molecule of those atoms, so you can't actually label it as a stereocenter. So we have one chiral center in there. Why is this not a chiral center?
Because it's sp2 hybridized.
sp2, planar, right? Carbonyl groups will never be a chiral center, but some of you will label them as a chiral center on the exam. So if you let me know right now who's going to label that, that'll save me time when I'm grading, right? Benzene rings can never be chiral because they're all sp2 hybridized carbon. Try to resist the temptation to label sp2 hybridized carbons as planar, even if they're attached to 3 different things. So this is the chiral center. What's the top priority substituent attached? N. Is that what you said?
Yeah.
Nitrogen. Nitrogen outranks carbon, right? This carbon's attached to oxygen, but that doesn't matter because it's the carbon at the first point of attachment, and we're not looking to the second point yet. So N is number 1. Hydrogen, of course, is always the big loser. Hydrogen even loses to deuterium, right, which is just hydrogen with 1 extra neutron. So hydrogen, yeah, it's total loser. So which of these 2 carbons is more important? And sometimes it helps to actually draw the hydrogens in so you don't like lose sight of the fact that there are hydrogens attached there.
Ketone carbon.
This carbon is attached to oxygen. This one isn't, right? They're both attached to carbon, but this one's attached to oxygen, and oxygen wins. Even if this was attached 3 times to carbon, if these were CH3 groups, 1 oxygen would still outrank the 3 carbons, right? It's not the total number of things it's attached to, it's the first point of difference. So there we have our substituents labeled. The ring going towards the ketone is number 2, right after the nitrogen. The ring, which is just a CH2 group, is number 3. Hydrogen is number 4. Now I need to put myself back behind the bond, so I'm actually looking up that way. So is that R or S, that stereocenter?
R.
S.
Okay, so we got both answers.
R.
If you're having trouble, one of the things you can think about doing, it's much easier to look at it if the hydrogen is pointing back. So what we could do is we could flip that 180 degrees, which would put that hydrogen back and the NH2 up front. And just keep our labels on there so we know. Oops, 1, 2, 3. So now the hydrogen is actually pointing back like it's supposed to because I rotated 180 degrees around the y-axis. And I think it's probably easier to look at now, right? Because now we're looking the right way down the bond. So it's fairly evident that that's the R stereocenter. You won't always be able to do that because sometimes the molecule will be big enough that drawing its mirror image is going to be a pain, or rotating it and redrawing it might be a pain, and you might get that wrong. But if the hydrogen is pointing out, if you're not very good at mentally putting yourself behind the molecule and looking at it from a different perspective, rotating it like this will help. On the exam, I would recommend you bring an R stereocenter and an S stereocenter with you. Just, tape numbers onto those atoms, and then you'll be able to take your R stereocenter or your S stereocenter that you've built ahead of time and overlay it on the molecule that's on the exam and see which one matches, because that'll save you some time. It takes a while to build models. And I would also recommend on the exam that you bring a cyclohexane ring with you already pre-built, or have it sitting on your desk already pre-built, so that then all you have to do is add the substituents to it in order to flip the rings and things like that. That'll save you some time. So pretty clear on how to do these things. I'm going to